Okay, so my name is Nikolay. I'm with TU Eindhoven, and this very short talk is about selected 3 topics that might be of interest to LDBC TUC. So let me just go ahead and let me just forge ahead. So me and George Fletcher, we are the principal researchers in our own database engine, which is called AvantGraph. And the idea of AvantGraph is it's a lightweight, close to metal, scale-up main memory graph analytics engine. So we concentrate on specifically on long-running analytical queries. And what we do is that we implement the cool stuff that we find from our fellow researchers and also the stuff that we ourselves come up with in this new engine. So in this short talk, I'm just going to give you a very short elevator pitch style introductions about 3 things that we implemented recently in AvantGraph. All right, so the first thing. The first thing has to do with cardinality estimations, which is incredibly important for query planning. And this paper, this survey that we just pushed onto archive is essentially a blueprint for the cardinality estimation framework that we have in AvantGraph. And in this particular survey, we focus on cardinality estimation property graphs. And that means not only estimating the topology, but also the data constraints and the combinations of thereof. And the idea here in this particular survey is to provide the explanation for different cardinality estimation techniques, going from RDF world, going from the relational world, and stemming from the basic principles. So think of probability theory. So have this comprehensive explanation of what's going on. Now, so in this particular framework, what we have is this general framework in which we can use existing work to produce cardinality estimation. And but also the idea there is that we're not only focusing on a single cardinality estimation technique, we can use multiple cardinality estimation techniques in order to obtain the estimation for a specific query. So for example, we start with a query pattern here, and then we can obtain a partial estimates, in here. And then these partial estimates can be obtained by anything. I mean, we can start with default values if you want, and we can go ahead and use a sampling approach to obtain cardinality estimation for part of a query. Once these cardinality estimations are obtained, we can then use assumptions, well-defined assumptions, in order to extend the this partial estimates to obtain the complete cardinality estimation. Now, the extension is typically based on assumptions such as independency assumption or the functional dependency assumptions. And all of these things we incorporate into this framework. Now, the main point here that we're trying to make is that we are able to compare several cardinality estimation techniques in one system, even combining them. And we would like to understand where do we get the error from, right? So what kind of assumptions are we getting the error from? Where does it all go wrong? And what are the costs of what are the associated costs with different cardinality estimation techniques? We have this on archive. For our experiments, we essentially translated joint order benchmark onto the graph domain. So we call this graph joint order benchmark. And we run comprehensive experiments on the state of the art of cardinality estimation to identify what needs to be done such that we finally get an accurate cardinality estimates, which concern both topology and data. All right, so that was the first thing. If you're interested, please look at the paper and we solicit your advice on this paper as well. So the second thing is, as already has been said, in a graph evaluation, and graph query evaluation, you often deal with very large intermediate results. And the one way to reduce such intermediate results is to start factorizing of the intermediate results during the evaluation. And for this, we have an approach which we call an answer graph, which does just that. So during the evaluation, we keep an auxiliary data structure, which is called an answer graph, which factorizes intermediate results. And this way, we try to essentially pre-filter the underlying graph before obtaining the final embeddings, so we can escape some of the those trillion size intermediate results during the evaluation. So this is the paper that was recently published at EDBT. You can also take a look. And in here, this data structure is really reminiscent of the good old Yakovets approach that uses semi-joins in the context of distributed databases, but now we use it at runtime. So we maintain this data structure by extending it, and we then can remove things which no longer will participate in the final embeddings by burning things off. This is the actual system. So we start with a conjunctive query. We obtain a query graph. We then obtain an answer graph plan. So how do we maintain this intermediate data structure? We then construct the answer graph itself. And this is supposed to be a much, much smaller version of the original graph, in which the edges do participate in the final embeddings. And then we use this particular graph instead of the original graph in order to obtain the final embeddings. In this way, we hope that we will pre-filter the original graph in such a way that we avoid an explosion in intermediate results, not only in the size of intermediate results, but also just in the time complexity that you have to look at those intermediate results. All right, so that's the answer graph, and we show that our approach is guaranteed to produce the fully reduced answer graph for the acyclic conjunctive queries. And this is a simple proof for that by using the GYO algorithm. But we can also work with the cyclic graphs with limited tree width with some materialization. So we also show how to do that. All right. So final topic is how do we handle an additional constraints in our database. And in this particular constraints, those are temporal constraints, so constraints that have to do with time. So these things show up all the time in graph queries. In practice, for example, identifying people spreading COVID is an example of such a query. And there's many constraints, temporal constraints, which are possible, of course. We concentrate on a specific type of a temporal constraint, which we call a K-click. So that means that we require in a certain time window for the query edges to all overlap. And having this query, we would like to optimize it and essentially push these temporal constraints into non-trivial join algorithms, such as worst case optimal joins. Typically, this is not easy to do because you either have to filter on temporal constraints first and then use your worst case optimal joins, or the other way around. So first get your topology done and then filter on time. But what we're doing, and this paper appeared in ICDE this year, we're essentially, so we modify a leapfrog tree join algorithm. So it's a well-known worst case optimal join algorithm to essentially push these temporal predicates into the algorithm itself. And that requires us to change the indexing, so not using tries, using something else, and to adapt the actual leapfrog tree join to process over this index and inject the predicates such that we can leverage full selectivity of topological and temporal constraints at the same time. And we also discuss a bunch of further optimizations. So yeah, and this is not all. So we're working on many, many things at TU Eindhoven in AvantGraph and also on other things together with George, who is here as well. And this is just a very small selection of master thesis and internships and other projects that we're working currently, which we already finished, and what we're currently working on. Okay, so if there's any questions, this is our team. Again, I would like to thank them for this contribution. We're lucky to have many good students here at TUE. And yeah, please, if there's any questions.
Thanks, Nikolay. We may have time for just one question.
I have one, but since I asked many.
Yeah, maybe there's somebody else in the room.
I wanted to ask you a question.
Sammy,
Sammy.
go ahead.
Hi, Nikolay. So is
Hey.
there a shareable system that's shareable with the community that's emerging that's you can share you could play around and then compare? Because I think there's several groups that work on similar techniques like factorization versus optimal. These are music to our ears too.
So we wanted to share a system, but then we got this benchmark from Gabor, and we realized that we still have ways to go in order to support all of the features in that benchmark. And then ideally, we internally made a decision that we would like to at least support everything that's there, and then we can share. So that's the idea. But yes, indeed, the idea of this thing is that it's going to be open source, right? So you can contribute, yeah, if you want to.
Okay.
Okay. Well, Sammy, in order not to eat into your time, I would like to thank Nikolay and his group for this update about AvantGraph.